Now, let's talk about thresholds in classification. And a good way to do this is to start with an example. So suppose I have two systems, and they get the following performance. I have system A, which has a true positive rate of 50% and a false positive rate of 20%. And then I get system B, which has a higher true positive rate, so it gets more of the positives classified correctly, but it also makes more errors. It has a 60% false positive rate as opposed to a 20% false positive rate. And the question is, if you had these two systems, which system would you prefer? Which system do you think is better? And you could start arguing, you could start thinking, well, you know, are true positives or false positives more important for my application? And based on that, you might prefer system A over system B, or maybe you have some other reasoning. Maybe you really want perfect recall or something like that. And the problem with even asking that question is the question is incredibly misleading, because it could be the case that A and B are actually the same exact system, the same exact classifier, just operating over two different threshold settings. So how could this be? And what am I talking about? We haven't talked about thresholds up until now, but thresholds are implicitly present in all of the classifiers that we talked about. Right? So think about the simplest one, right? Naive Bayes. So what do we do with naive Bayes? With naive Bayes, we compute the posterior probability of positive. So we compute the probability that the email is spam given the vector of word occurrences. Right? And that probability is a number between 0 and 1. And then what do we do with that number? We look if that number is bigger than 0.5. If it's bigger than 0.5, we classify it as spam. If it's smaller than 0.5, we classify it as non-spam. So that 0.5 is a threshold. With naive Bayes, it's explicit, but almost every other classifier also has a natural notion of threshold built in. So most of the classifiers that we have, what they really do is they compute some sort of a confidence function or output f of x for an instance x, and then they compare it to a certain threshold setting. So for naive Bayes, f of x is just the posterior probability, and the threshold is 0.5. For linear regression or logistic regression or support vector machine or any linear method, you have a weight vector w. You multiply it by your feature vector x, you get a number. And then you look, is that number positive or negative? If it's positive, I'm on the positive side of the decision boundary. If it's negative, I'm on the negative side of the decision boundary. So that's straightforward. But 0 is just a number. I could have picked any other number. I could have said W transpose X greater than 0.5, for example. And I could have taken this and said, okay, it's not 0.5 that I want, but 0.7. I want to be really sure that it's spam before I send it to the spam folder. So I'm going to artificially raise the threshold. It's also present in decision trees and just about everything, every other classifier that you have. So, and it's this threshold T which we have brushed under the carpet until now. That's what really determines the error rates. That's what determines the false positives and false negatives. Why? Because think about it. What is a false positive? A false positive is something that was really negative, an email that was not spam, but our system thought that it was positive. Now, why would our system say it's positive? It's positive if the function f of x, the confidence, is bigger than a threshold. So really, the false positive rate, it's just the probability that your confidence function exceeds a threshold, given that you're in the negative class. And your true positive rate is the probability that you exceed the threshold, given that you're in the positive class. Okay? So the true positives and the false positive rates, they are functions of a threshold. And as you change that threshold, you can get radically different values for true positives and the false positives. So let's look at an example. So suppose I have a spam classifier, and the x-axis, that represents the confidence of my classifier. So the higher numbers to the right, my classifier is more confident that they're spam. The lower numbers, it's less confident. The green documents represent documents that, emails that are really spam. The gray ones are emails that are really not spam. Now, what happens if I set a particular threshold? When I set a threshold at a certain value, say I set a threshold at T1, I'm splitting the data into two parts. Everything that's to the right, my classifier is going to say they're positive. Everything to the left, my classifier is going to say they're negative. And it's going to make some mistakes. So everything to the right, my classifier thinks they're positive. Some of them are really positive, so I have 1, 2, 3, 4 true positives. My classifier thinks they're positive, and they really are. And I have 1, 2, 3 false positives. My classifier thinks they're spam, but they really are not. So in this case, my false positive rate is going to be 3 out of the total number of negatives. The total number of negatives is 15. So it's 3 out of 15, so it's 1/5 or 20%. And my true positive rate is out of all the spam emails, there are 8 of them, how many did I classify as spam? 1, 2, 3, 4. So I have a true positive rate of 50%. Okay? So that's my true positives and false positives. And I can also compute the false negatives and the true negatives. They are things that lie to the left of the threshold setting. Now, if I happen to take that threshold and put it in a different place, I get a very different picture. So if I set it at T2, everything to the right, my classifier thinks it's positive. Now, all 8 of the spam emails are to the right, so my recall or true positive rate is 100%. But my false positive rate is higher. Now I have mistakenly misclassified 9 out of 15 non-spam emails as if they were spam. So my false positive is going to jump to, what is it? That's actually 60%. Okay? So now, realize the only thing that I've changed is I've changed the threshold setting. I haven't changed my classifier at all. It's the same classifier, you're just moving the threshold up or down, and based on that you can get very different false positives and true positive readings. So the question, is this one better than that one? It's a moot question. They're not comparable. I can make this one that one just by moving the threshold up or down. It's not a well-formed question. A receiver operating characteristic is a type of evaluation. It's a type of a graph that tries to take threshold out of the equation for evaluation. The basic idea, what you do is, instead of setting a particular threshold value and then computing true positives and false negatives, you try all possible threshold values. And you plot the results as a function of a threshold implicitly. So that's what it usually looks like. So what I'm going to do is I'm going to set a threshold very, very high initially. Right? If I set a threshold right here, what's my true positive rate? 0. Okay, what's my false positive rate? No, it's not 100%. My false positive rate, if I set a threshold right here. So false positives, what have I classified as positive? Everything to the right. Is there anything to the right? No, it's 0. So my true positive rate is 0, my false positive rate is 0, so I'm going to get a point right here on the graph. Here I have the false positive rate, the true positive rate, okay? Now I take this threshold and I slide it 1 over. What's my true positive rate? 1/8. What's my false positive rate? 0. I haven't added any positives. Okay, I slide it. My true positive, 1/8. My false positive, 1/15. Yes, okay, you get the point. I keep sliding it, and I'm going to get different pairs of true positives and false positives, and I'm just plotting it. And then here, when you have lots of them, they form one smooth line. And that line is a representation of the accuracy of your algorithm over a whole spectrum of thresholds, going from positive infinity, really high thresholds, to negative infinity, right? So in this case, my true positive rate has to be 100%, because all the positives are to the right. My false negative, so that's the true positive. My false positive is also 100% because all the negatives are also to the right. Okay. So you're going to get a curve that looks like that. Now, this plot is neat because you can learn lots of other things from it. For example, if you get a line that looks like that, that is perfect performance. That is the best classifier that you could ever get. Why is that so? Just think about it for a second. What is happening at this point? This point corresponds to some threshold where all the positives are on the right side of me and all the negatives are on the left side. So at this point, I have a true positive rate of 100%. I've classified all the positives correctly. They're on the right side. Okay. And all the negatives are on the left. So I have a 0% false positive rate. Now, if I move the threshold a little bit to the left, I'm going to increase my false positive rate. If I move it a little bit to the right, I'm going to decrease my true positive rate without affecting the false positive. So as I move to the right, I'll be moving down this line. As I move to the left, I'll be moving to the right. So that is the curve that gives that results from a perfect classifier, a classifier that that can completely separate the data into positives and negatives. And that is a completely random classifier. So if you have a system that is completely random, it will have an ROC curve that looks like that. And if you're trying to get an intuition for why this is happening, imagine the system that has equal number of positives and negatives in your task, and it's just alternating, one positive, one negative, one positive, one negative, one positive, one negative. So the curve is going to move in little steps like that and straddle y equals x. Next line. So ROC curve, really nice tool for taking threshold out of the whole equation and seeing how your system performs over a whole span of thresholds. And of course, if you set thresholds to particular values, you get points on an ROC curve. And if you have two different systems, so you might have A and B and C, and you're comparing three numbers, and comparing just pairs of numbers is difficult. But if you plot an ROC curve, you can quickly conclude that the blue system is a lot better than the orange system, because no matter what threshold setting you pick, the blue system is going to have a better trade-off. It can replicate anything that orange system can do and be better than it, right? So for any given false positive rate, it can get a higher true positive. For any given true positive threshold, it can result in lower false positive rate. So it's a useful tool for comparing systems. Another single number metric that's commonly used is instead of accuracy, you take the ROC curve and measure the area under it. So that area is basically just the area. So for the perfect performance, the area is going to be it's 1. So it's the area under the curve, not over the curve. And it's 1 because this ranges from 0 to 1, and this ranges from 0 to 1. Right? And for a completely random, what's going to be the area under the curve? 1/2. It's not 0, it's 1/2. And by the way, you can get systems that perform worse than random. It is possible.